if I had this covered up right now, would you at this point know what that means? Curly E. You should be looking at curly E and saying, ooh, that's field intensity, right? And that's how much force there is per charge. Okay, so that's something that should be sort of recognizable at this point, is that curly E, right, equals this stuff. That's ugly. Equals this, right? So we're talking about like force per charge, newtons per coulomb. So that probably says something like that in here. Oh, actually, we're just solving the equation at this point. So we're solving for the electric force so that we can put the force value into the work concept. Okay, so we're just saying, oh, well, the electric field intensity of this thing, if you know the electric field intensity. Okay, so basically here, there's going to be a known electric field intensity. Or let's say we're given. So we're given the electric field intensity, which we know, of course, is curly E. So i.e., let's say here, some number, which is in newtons per coulomb. Hey, David, how did you do a curly E, by the way, on the email or text message, whatever it was you sent me, message you sent me? Where's curly E show up in the device?
I just Googled it and copied and pasted it.
Oh, okay, I see, that would work. So when I was messaging you back, I was like, typed in curly E, so like, I don't know where to find that on my phone's keyboard when I'm typing into the Teams chat window. Pretty slick. Google it, copy and paste, good stuff. Anyway, so the curly E times Q can go in for force, right? So just recognize there, that's what we've got. We've got, how do I gonna do this? I'm gonna do it with purple. So we've got the force, there it is, right? Because we know the force equals QE. Just to try and help that page, help you follow along what's going on. So now we've got a curly EQR for work done so far. Go ahead.
I'm sorry. So the F and like the FE, are they the same thing?
Yep. Yep. Because the work done in the situation between the plates is work done is by the electric force.
Okay, sorry.
No worries, not at all. Don't be sorry. Just ask away. That's what I'm here for. So now this is where I'm actually talking about that dot product. I knew I did on this page somewhere. I just got lost track of where it was. But dot product is actually the force in the direction. It gives a scalar quantity, you know, and so on, right? So this scalar result of work comes from this mathematical process of multiplying the two vectors, the sizes of the two vectors. And so since we know that work done is delta E, that's fundamental, right? That's very basic stuff, like work done and delta E are the same thing, but we know this equation here as well, right? That the potential difference is equal to the change in the energy per charge locally from A to B. That means we can put that in to it as well. So we're substituting now delta E, you know, into here. So that's really just delta E again, but now in terms of the electrical information. So we can work towards this. This is that, by the way. You know, the actual potential difference between two spots is the potential at two spots subtracted and so on. Like that's what we've done before. It's just a reminder of, like I said, recall here, right? So it's a reminder of what we've done. And so that gives us, notice here, how did we get to this? How did this happen? How did we get to this? All that happened was we noticed that we can divide both sides by Q, right? So just divide both sides by Q, and that goes away. And so now we're saying, oh, so delta V equals the field intensity times R, right? So if we want to talk about field intensity of between two parallel plates, we just solve for curly E. That looks like an upside down 3. Anyways, solve for curly E, and you get the voltage applied across the plates divided by the distance between the plates. Okay, so we're talking about, yeah, it's actually the magnitude, of course, because we're talking about the dot product definition I noted there. So that's the expression that you can box in now. Like I hope you've got a page going where you like write down equations. And I really like yesterday's lesson when I thought of on the fly there, showing like we've talked about force, and then we talked about field intensity, force per charge. Then we talked about energy. We talked about energy per charge, and then we, like just all these concepts and the associated equations. You're gonna want to have those on a nice page so you can refer to them and help keep your head straight as to what the heck we're talking about. Okay, we're almost done this section. Like we're almost done electric field stuff, which is the good news, right? But I still feel there's a fair bit. And when you look at a question, you have to kind of get your head around what the heck we're asking. Like 8b, for example, being about electric potential instead of 8a being about electric potential energy. There's a subtle difference between those two, and it changes how you do the work, how you do the calculations. So a page like the one that we did on the 16th, I don't know which lesson it was. Wouldn't be the copy anyways. So anyways, you remember I did it. Next step, or if you don't, then go back and watch the video. So this is just not that big of a page, but basically it's like saying like, oh, so if the distance, since the potential is proportional to distance, like if you had the distance between the plates, what does it say? If charge moves 1/3 the distance between the plates, and you're gonna have 1/3 the amount of energy. Like it's just, that's the idea of pointing out the proportional things like we've done in the past. So I want to spend a little bit of time just talking about that contradiction thing. So the apparent contradiction between previous statements about electric fields between parallel plates and this new one. Most textbooks don't explain this. I personally was actually a bit bothered by it for years. I actually had the opportunity to talk to a professor at one point about it, and I was like, okay, how come it says sometimes that the fields are not depending on the space, the distance, but now we have this equation that says they are, the electric field intensity does depend on the distance. And the way it was explained to me is the way I explained it to you previously, is that if in the case where we had the fields where the charge was just built up, not with a voltage applied still, then it actually takes energy to push them further apart because they're attracting each other, right? And so the fact that we have the same force over a longer distance, I feel like I should draw a little bit here. So go back to the idea of parallel plates with charge built up. We know that on an electron, there's going to be an electric force, right? And so if you look at the distance that force applies over, like this, delta D, then you'd be like, well, work done, or the amount of energy there is, right, is going to equal the force times the distance, F delta D. So we've got the electric force times that distance, and so on. So, if in this force, if we move this plate apart, so let me just do something here. Looks like it's already, yeah, it's perfect. So we had it here, right? And then basically, what we've been told in the past was that if I move this plate out to here, so I'm gonna make this one dotted so you can see that it used to be there, right? If I move that out, we get more displacement. More delta D, which means more energy, right? So more delta D means more energy, right? So to me, it's like, okay, so I feel like we must have had more force, right? But it's not more force. Or less force, actually. I should have pointed out we don't need more force because of course we got the more distance, right? So it's the Fe remains constant, right? So the curly E is not dependent on delta D, the space between them. I've been saying delta D here, but these all could be R's, right? So this could be R, this could be R, this could be R, R, R. We often use R, right? So we've said in the past that the electric field intensity remains the same, doesn't depend on the distance between, which seems odd, but you have to remember that this right here, so let's go with black. When we do this, that's supposed to be black. Come on, do it, right? So this takes work. So when we add the extra energy to the system, well, that explains where the extra energy is coming from, right? So the same force over a longer distance is giving more energy, but that doesn't mean there's a greater field intensity. It's the same field intensity. Now, this part here, E is not dependent on R, as long as, right? As long as the area of the plates is large relative to the space. No one ever said that to me either, relative to R. You know, so it seemed to me like, so I can just take these parallel plates, move them like kilometers apart, and the electric field's the same between them. Yeah, right. My problem was I just didn't believe it because, of course, it's not true, right? So I was being too literal about it. But, you know, as soon as someone says to me, oh, well, as long as they're not too far apart, I'm like, oh, okay, that makes sense to me then. Okay, so this is parallel plates with charge built up. Trying to type here. Parallel plates with charge built up. Put in there no applied voltage anymore. Okay, so that's the situation that we have talked about in the past. Okay, so if you're looking back and you're trying to review this stuff or anything else, and you come to today's lesson where it says electric field intensity is the voltage divided by the distance between, you very well might say, well, wait a minute, didn't we say that it doesn't depend on the distance? It's a different situation. Okay, so the situation we're talking about now is the one where there's a voltage applied. So what I just explained is all on this page as well. So we learned earlier that blah blah blah. That's the electric field is proportional to the charge on the plates, but not the separation distance does not affect the field, right? So this new equation seems to contradict that. So the difference is highlighted here if the battery voltage creating the charge separation in the plates is kept constant, right? If you have a voltage applied, then the distance between the parallel plates needed to affect the electric field intensity, it changes. Basically, the amount of charge on the plates actually changes. The battery is not able to push electrons all the way out effectively to the other side of the plates once you move them. Okay, so moving the parallel plates when there's a voltage affected actually affects the amount of charge that's built up, and it does affect the electric field intensity as a result. Okay. So capacitors are common. Parallel use of parallel plates, they store energy. Little capacitors, they're really just a big coil of usually they're a coil of a flat metal sheet and with a space between them. And so basically you've got a parallel plate that just conveniently is rolled up so that it fits inside of a little cylinder. So you've got parallel plates. I'm trying to go to this page here. You've got a space between two metal surfaces. Once you have a whole bunch of charge, two plates, I guess, right, rolled up together. Once you have a charge built up on one and the other, they have this potential difference between the two. You've got energy stored. So it's a common way to store the big burst of energy needed for a flash in a camera, right? In old school cameras where they actually flash rather than just like shine an LED light like iPhones and whatnot do. When you have a camera that flashes, that energy is a big burst and it came from a capacitor. Another example is with air conditioners. Air conditioners have capacitors to help them get the big burst of energy they need to start running. To get an electric motor running is in the compressor is difficult, needs a lot of energy, and so capacitors are in there to store it. So if your air conditioner just stops working this summer, there's a really good chance it just needs a new capacitor. I've had that happen. 2 summers ago, I think our air conditioner stopped working and just needed a new capacitor. It was all it was. This equation also reminds us of electric potential energy difference is dependent on the distance. Yeah, it depends on the distance, like we said. So the trouble with this is clarity, really. A lot of times they don't really tell you, is this a situation where there's a charge built up on the plates, or is it a situation where the voltage between the plates is constant? Sometimes textbooks in general, or people sometimes are a bit vague about which kind of situation it is. There's 2 different situations. Okay, So let's just say here, this one electric field intensity is proportional to the voltage only. And then in this one, right, it depends on the voltage divided by R, or we've got a voltage applied between them. So my hope is that you will not be confused about this for as many decades of your life as I was, because I was confused by it in grade 12 physics. I don't know if I didn't ask or whatever, I don't know. But anyways, it bothered me always. And then I went through university and no one really explained it. It wasn't until like after university, I think I started asking better questions also, right? As I was learning it and getting to understand it better and teaching it. But I had, like I said, I had a chance to ask a university professor at one point, and they explained it, and I kind of understood at the time when he explained it, and I went and thought about it more afterwards, and now I'm feeling good about it. So keep learning, basically, is a good message. It's okay to keep learning. And anyways, any questions right now?
Sorry, do you mind going back to the last slide? I didn't get the last bit.
Sure.
Thanks.
Let me know when you're ready.
Okay, good now.
Awesome. All right, so basic question, if you have this new equation, you've got a parallel plates and you've got a 1 centimeter distance between, of course, we're going to convert that to meters, and I'll just show that here since they've already done it, right? But there, just divide by 100 because there's 100 centimeters in a meter. And give the voltage, and so you're like, okay, well, that's the voltage applied across the plates, and we're okay with listing it as delta V, even though in grade 9 we didn't do that. And yeah, so we just have our new equation, curly E equals delta V over R, plug in the numbers, get an answer. I feel like maybe you might want to just like, I don't know, take a screenshot of that or something, but it's like the basic kind where we're just plugging in numbers, getting answer. Okay, so I don't want to dwell on that page too much. Just know, of course, that we plug numbers into the new equation. So whatever two you're given, you can solve for the third one, of course, right? So I think just recognizing, recognizing words here. It's like, oh, potential difference, that's this. And then they said, oh, the distance between, or actually the voltage applied. Let's focus on, yeah, actually, those should all be red then, right? So potential difference applied between two, that's the red stuff. And then the purple was, of course, the distance apart. And then when they're asking for the electric field strength, you got to recognize that's what they're asking. Right, field strength, force per charge.
Mr. Horn.
Yeah.
For the answer for that one, why do you have like the N and the C there? Like, what is that?
Newtons, yeah, Newton per Coulomb. So that's a unit analysis. Good question. So basically here, see how this is obviously volts, right? And then this is obviously meters. So the units are kind of like volts per meter, but what the heck does that mean, right? So then you look at it and you'd be like, okay, volts per meter. And I'll show you, that's the same as newtons per Coulomb, but that's not obvious, is it? Right? But you can tell that it should be newtons per Coulomb more simply because like we're talking about, electric field intensity. So it's a great question you're asking, because basically what I'm taking it as is you're asking how the heck is volts per meter the same as newtons per Coulomb, right? So what we can do is we can just analyze the units of each of these and see that they're the same. Might be the best way to do it. So for example, volts we know is electric potential, it's energy per charge, right? So when we're analyzing this out, we can say, okay, volts is the same as joules per Coulomb. So that's the volts, right? And then on this side, maybe we could say, okay, you know what? Newtons, that's force, right? And we know that F equals ma. And so depending on how we want to do this, but yeah, F equals ma. And so that is kilograms meters per second squared per coulomb, right? And then we could recognize that joules is energy, right? Which we know is force times distance. And so it's a little crazy, but you know, force again is kilograms meters per second squared, right? So I'm going to change the J to be kilograms meters per second squared. I'm going to write it like that this time. I probably should have done it over there too, times meters, which becomes kilograms meters squared per second squared. So kilograms meters squared per second squared is the J, and then that's supposed to be still over coulombs, and then that is over M, right? So the final step here then is to say, oh wait, so if I've got an M dividing it into an M squared, the squared goes away, and so it looks like I'm left with kilograms and meters, and I'm just checking as I go here, see my mouse pointer, so kilograms and meters and per second squared, and then the bottom we're dividing by coulombs, right? So what we have done there is we have confirmed that these units, the unit for force per charge and the unit for volts per meter, are the same, right? So volts per meter really is newtons per coulomb. So you can see the importance of sort of having this idea of SI units and how, you know, velocity is really meters per second, and force is really, you know, mass times acceleration, kilograms times meters per second squared. Like having understanding of all of those fundamental units allows us to double check to see that that really is true. So thank you very much for asking that question. That's a really good thing to have asked if that's what you know, assuming that's what you were meaning, but you were questioning units, right? So does it help?
Yep, exactly. Thank you.
Good. Great question. It's kind of strange, right? Like it's sort of very mysterious, and you're certainly not going to do this all the time, right? But once in a while you do this and then you're like, okay, cool, I get it. You know, so when I calculate using this formula, curly E, the answer really is newtons per coulomb, which, just to emphasize something that should be known now at this point, right? We're going to emphasize here that note, you know, this is force per charge, right? So it's newtons per coulomb. And so that's basically going for, come on now. So force per Q, so newtons per coulomb. And so that's really what you can do from now going forward. But that was a really good activity for us to go through, though, to show you the power of understanding what the base units are for everything. And it helps you understand how these new concepts all mesh together. Good stuff. So, you know, here's a question. Negatively charged particles allowed to move freely in this parallel plate apparatus. If it's given like that, well, I didn't get all of it, but you know, if they don't show you that, to me, it's not a good enough question. They should be obvious, right? Anyway, so if a negative particle is allowed to move freely in that apparatus, which way will it go? So you're like, okay, you stick a negative, actually, let's just do Q negative in here, Q with a negative sign. And you're like, okay, well, where's that gonna go? Well, of course, it's going to attract to, if I can regain control of my screen here, my mouse, right? It's going to attract to the positive, so it's going to go this way. So because of the voltage, so I'll use the purple, but it's going to go that way. Where would it have the most electric potential? What does that mean? What does electric potential mean? It means energy per coulomb, right? So I don't know if I have room to write this in here. Energy per coulomb. So that's a little sloppy, but the big kindergarten thick writing is hard. So this is energy per coulomb. Let me do this again. This is energy, go blue, this is energy per coulomb. Right? Joules per coulomb, in other words. So where does it have the most energy per coulomb? Well, it's going to have the most energy per coulomb at this spot right here. Why? Because that's where it has the energy that we know is going to be released to kinetic energy, right? So at star, let's say at star for now, and the answers are on the next page all worked out, but at star, right, it has all energy as EE, right? And then, of course, it converts, right? It converts to BEK. So picture it slamming into the positive plate with a whole bunch of kinetic energy. The electric potential per coulomb, energy per coulomb, has transferred into kinetic energy. Where will it experience the greatest field intensity? Trick question, right? We know that it's constant. E is a constant. So it's the same intensity everywhere, except, of course, out here, right? There's a little bit of bulging at the corners, and this is as long as the plates are big in comparison to the distance between them, and there's all sorts of restrictions, but roughly speaking, it's the same electric field everywhere. If the potential difference is 120, so now they're actually saying this this thing. So they at least said it, but to me it should have been in the diagram, right? So if electric potential difference is 120, then at what point will the charged particle have experienced a potential difference of 40 volts? So that's just a, an understanding numbers thing, right? We're going from 0 to 120, and they're saying, where is it going to become 40? And you're like, a third of the way. Like it's 40 is 1/3 of the way. $40, $80, $120, $4, $8, $12, right? So 1/3 of the way. If the distance between the plates is reduced to half of the original value, and the resulting electric field strength between the plates is 65, determine the original distance between the plates. I made this question. We're going to do this one on the separate page. Determine the original distance between the plates. Okay, so let's just confirm all these things. It says which way does it travel? Well, it'll travel from B to A, of course, like I said. It'll have the most electric potential near plate B, because at plate A it has 0 potential. That's energy. That's EE, right? They're talking about electric potential there. They don't sometimes say electric potential, but that's EE per Q, right? It will all have transferred to kinetic, and that's what it says up here, right? This is where electric potential energy stored and available, up down at B, right, is where it's stored and available to be released, right? It will accelerate as it repels from the negative plate, and delta EE, so this acceleration and repulsion thing, right, leads to basically a delta EE becoming a delta EK. So, and actually, soon we're going to see a question where we're going to say negative delta EE. In other words, you get if you lose or the electric potential energy goes down by 100 or something, then this one's going to gain by 100, right? And so you're talking about negative of that drop equals the positive. So negative of negative 100 equals positive 100, right? Because it's a drop in electric potential energy corresponding to a gain in kinetic energy. Where does it have the greatest field intensity? Of course, it's the same throughout, and 1/3 the way. So that's all good. Now this question number 5 says if the distance between the plates is reduced to half the original value, okay, and the resulting electric field is 65. What I'm saying in my solution here for that is that we know that electric field intensity depends on the distance between, right? And so if the radius, the distance between was divided by 2, then we've got our classic, change R to be R divided by 2 and see what happens, right? Of course, we invert multiply and end up with double the electric field intensity. Okay, so the new electric field intensity is double the original, the 65, the 6.5. What did I give it as? 6.5 times joules per I should have said, yeah, you know what? I started with 65 and the numbers were ridiculous. And so I changed it to 6.5 times 10 to the, so this should, in my original question, should read as 6.5 times 10 to the 5. I'll remember to change that in my copy of the lesson. Times 10 to the 5. I started with a 65 Coulomb just to see what happens. And when I calculated out the distance between, it was ridiculous. And so I then chose a reasonable distance and calculated out what the field would need to be. Anyways, so that led to this conclusion down here, where the original one must have been half of that, right? Because the new one's double the original one. So I took half of it and said, okay, so the original one must have been 3.25 times 10 to the 5. So how do we figure out the distance between the plates then? Well, look at this formula right here, right? We now know we're given the applied voltage originally. Now we actually know the electric field intensity, right? And so we can plug in the field intensity. We've got the applied voltage. We can figure out what the distance between the plates must have been. Boom. So the original distance between the plates was 0.000369 meters. In other words, like it's whatever that is in millimeters or whatever, 0.3, 0.4 of a millimeter. Very realistic, actually. Kind of a tiny little space between the plates. So with the assistance of the associated video from this lesson and the worked solution, I'm hoping you can master this and with confidence be able to sort of work your way through these things. Okay. Yeah. Any questions at this point?
I'm kind of confused over 5 and 6.
So
I'm trying to think of like a question to ask, but
honestly, I think it's just going to take rewatching the video, going through the question again, even stepping back and reminding yourself what the heck we just learned, right? So we went through this analysis and decided or proved that the electric field intensity, the force per charge, right? That's part of what you're asking is you need to sort of get to the point where all of this is automatic for you. So you're like, okay, that's force per charge and equals the voltage across the plates divided by the distance. So when you read this question, right, when you read this question here, I guess it is, yeah, they were like, okay, they gave me the voltage, and I'm being told the field strength. Ooh, this is supposed to be newtons per coulomb, not joules per coulomb. So this is, it's easy to make little mistakes like that, and it just in textbooks do it too, and then students are bothered by it, So let's fix that and recover from that. We're talking about field strength. That's force per charge, right? So that should have been listed as newtons per coulomb. So, again, so we're given the newtons per coulomb, that's curly E. We know the voltage, so that's where in number 5, I was able to, or number 6, I guess, right? Which one would it be? Kind of here, I guess, we ended up knowing the field strength. So number 5, we have that in-between step of saying, like, what happens when we whatever I said we're doing to the plates here, up here. We are reducing the distance to half the value. And so the new equation we've learned today, right, you recognize like, oh, if they're closer together, it's going to be stronger, right? Shown by this right here. So this is like half the distance now, right? R over 2. So the R over 2 went in, and algebraically you solve it out. And my goal here is actually to get you used to the idea that you separate this number, right? Separate this number out so that it's out on its own. And then you have the luxury of being able to say, okay, well, this is curly E, right? And so like you're saying curly E new, right? The new curly E is equal to the old curly E times 2. So that's why my conclusion is the new one is double the original.
how come the new one is double the original when it's the one of the plates are just charged? I thought that the curly E was only different when they were like applied voltage.
But this isn't just charged plates, right? This is an applied voltage of 120.
Oh, okay.
Okay, yeah, that's fine. So you're absolutely right. If it was just charged up plates, then basically the answer would have been, right? If this was up here in number 5, if it was just charged up plates, then the answer would have been the field's the same. And you're like, all right, weird, right? That they're so different, but that would be the correct answer for if it was just charges on the plates versus having a voltage applied. And
that makes more sense. I think I was confused over, I didn't realize that the voltage was applied.
Totally understandable. Totally understandable. There's such a subtle difference, and it's such a huge difference as a result. It's crazy. But yeah, and then so at the end we had the field intensity, and we're like, oh, I'm gonna solve for the distance between. That probably wasn't the part that was bothering you, though, was it? Cool.
Yeah, no, it was more 5, but I got it now. Thanks.
Perfect. Thank you for asking. I'd much rather people ask than just sit on the other end frustrated and crying, because I can't see if you're crying, right? So let me know if you need help. All right, so we've talked about this a little bit before. I'm just gonna just go through this fairly quickly, probably as a result. But the idea, the concept of this oil drop experiment is if you had like 10 sealed bags and there's a bunch of marbles in them, and you're like weighing how much, like seeing what the mass of each of these bags are, and you know there's like a certain number of marbles in each bag, and you have a whole bunch of masses, right? Then you know it says your challenge is to figure out the mass of one marble, right? So you look at like the smallest value here, and you know it's possible looking at the smallest value that'd be one marble, but then you're like, oh, that can't be, because then all the other ones would be either 10, 20, 30, 40, right? So basically there's some small number that these are all a multiple of, and that's exactly what Millikan deduced from his oil drop experiment. So the marbles have a whole number mass, and so you're trying to think like, okay, what whole number could make a 16 and a 24 and a 20 and a whatever? And I think it's like slightly smaller than one of these. And it's not, some people are better at numbers than others, right? I personally don't look at that, and it's not obvious to me, but I bet there's someone in the meeting right now that's like, oh, I can tell. Anybody? What number could you multiply by 1, 2, 3, 4, 5, 6 and get each of these numbers? Well, except for the 1, of course. No? I usually have students around that some people are just kind of good with numbers. They're like, oh, I can tell it's a 4, or I can tell it's a 8, or whatever.
They're all even.
They are all even. That's a big
even, so probably 2.
Yeah. So let's say all even for sure. So that's a big hint, right? They're all even. That's an excellent thing to notice. So then if they're all even, it could be 2 for sure. So it could be 2. Could it be anything bigger? I'm not sure. Could be 4. Could be 6. You know, basically, and just narrow it down, right? And so the smallest one could be maybe 4 or 6 or whatever, but certainly 2 was eligible as a possibility, right? So I think it ends up being 1 or 2, right? And so because there's only ever evens, that was a great thing to notice. Since they're only ever even, you're probably going to be 2 then, right? So it's, you know, if you kept measuring and you found a bag of marbles that was 2 grams, you'd be like, aha, you know, that would really confirm things, right? So that's what they had to do with the Millikan's oil drop experiment, is they're faced with that challenge of trying to figure out what that smallest number is. So Millikan ended up measuring and figuring out that the charge was 1.602, right, times 10 to the negative 19 coulombs, which is pretty cool. So he also concluded not only that that's the charge of an electron, but he also concluded that that's the smallest charge possible, which was a bigger thinking question, right? That was kind of thinking outside the box, thinking, oh, that's the smallest charge actually possible overall. And he had other things in his mind and what he was worried about and thinking about that sort of led him to that as well, to do with quantum physics, right? Quantization of matter and so on. But that was early yet. Like he didn't really have a ton of that wasn't developed yet at that point, but he was kind of on the leading edge there thinking about it. Yeah, so the oil drop experiment we've talked about a little bit, and we've seen a little bit about it, but we have this like parallel plates and an oil drop suspended and so on. So I'm just going to talk about the ideas of it again just briefly here. But of course, the oil droplets went through the atomizer. They automatically pick up a little bit of charge due to friction. That's what happened when I was doing it. We didn't have a voltage applied to the oil droplet sprayer or anything. I think I showed before that you have a sprayer, you have oil droplets going out. Well, if there's a bunch of negatives, if this is just charged a little bit on its own, these negatives will repel and end up on the oil droplets, right? So parallel plates were oppositely charged, and then basically you make the negative plate be on the bottom and adjust the voltage until you either suspend the oil drops or have them go at a constant velocity. Either way, you're essentially balancing the gravity force with the electric force, right? So the bottom plate equal and opposite to gravity. Basically, this is leading to Fg equal to Fe, right? And once you know Fe, then that's going to allow you to figure out the charge on electron, because we know, Fe per Q is going to be like a known value. That's your curly E, and so on. I almost put a Fe per Q would be your curly E, and etc. Right? So you can see how they'd be able to work towards this. I'll show you the steps, but there is some vagueness to this in terms of like actual, like I'm not going to carry out all the steps, but the idea, we said, like if they're suspended or have constant velocity, then the net force is 0. And so since the only forces on it are electric and gravitational, we're quickly getting that conclusion that the electric force and the gravity force would be equal, I suppose equal and opposite though, right? So I should add a negative there. But if we just said magnitudes, then that's fine, right? So if it had been magnitudes, certainly they'd be equal. So we know that equation right there. I want you to recognize that you're saying, okay, you know what? I'm good with curly E equals Fe per Q, force per charge. And so that becomes this equation, of course, right? And then we've got gravity is mg. So we've got curly E, Q times curly E is equal to mg. So, fairly easy substitutions as we go through the ideas of this. Then you're like, ooh, I remember from parallel plates that curly E is delta V over R. So we've got Q delta V over R now, right? This is just curly E plugged in. So rearranging, we want to get Q, of course, right? We're looking for the charge and electron. So rearrange, and you've got mg R divided by the voltage across the plates. The voltage across the plates is for sure known. The distance between the plates is for sure known. Gravity is for sure known. The unknown here at this point is the mass, right? So the mass is the part where I'm flubbing a little bit, and it's complicated and annoying, and it involves estimation. It's a estimation of the radius of the droplet. You end up using the density of the oil. And so basically you estimate that mass of that oil droplet, and as a result get an estimate for the charge of the droplet. And that's where you end up with a bunch of numbers, a bunch of multiples of the actual charge and electron. So the annoying part of this experiment is really actually that. It's actually that's the part where you're like, I hope I estimate this well. And you just, with practice and repetition, you get more and more consistent numbers, and you get a measurement of the charge and electron. So I've done this experiment. It works. It's kind of neat. Yeah, so this video here describes everything I just talked about, but you can visualize it a little bit better too, and seeing it. I'm not going to play the whole thing or anything, but first we'll get an ad from Grammarly, I'm sure, but I'll come back to it once it's ready to go here. Probably hear it.
Millikan's oil drop experiment.
Yeah, there we go, just then give up on it.
British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that
I should add too, by the way, they don't show it here, but this one here,
R.A. Millikan looked to determine the charge on
sorry, this guy here.
In charge to the mass of an electron using a cathode ray tube.
So
in
that one they would have actually
1897.
been measuring. I can't stop it. There we go. They would actually be measuring how much it turns as you put an electric field on it, and that's how they got the mass. Anyways, but he's like, oh, you're working with electrons. I can work with electrons too, and so he did the whole droplet in between the plates thing, and yeah.
Using this method, he calculated that the charge on an electron was about 1.6 times.
Go just a touch here.
Using this metron is known as the Millikan's oil drop experiment. Using this method in 1914 to measure the charge E of an electron is known as the Millikan's oil drop
Whatever.
experiment.
I've explained it in enough detail already, but to visualize it, that video is there for you. So just a little bit more from this one. So if you decided to carry this out and you had plates that were 5 centimeters apart and you had a spherical drop that you know the mass of, remember that was the hard part, so if you're given the mass, you're good to go. And you know the voltage that's applied, and you make the top plate negative, which is kind of weird. I don't know why that was decided, but basically that means that your oil droplet is going to have an excess or a deficit. If the top plate's negative and it's accomplishing the goal of slowing the fall down or even suspending it, then the droplet must be attracted to that top plate. So it must be positive, so it must have a deficit, right? It must be a positive droplet. So you'd have this, and you'd have a positive Q with an electric force on it. So that's part C answered already. What charge? Oh, what charge? Positive. And what's the magnitude of the charge? So the magnitude of the charge is trickier. I'll just go through it. But obviously, we're given those things, the distance and the voltage and so on. And there's the idea of the charge, the equation that's to do with this. We know that this is just basically going through that development again. Obviously, you could just use this equation if you know it, right? But the deal is, if you don't know it, well, you do know this, and you do know this, and you do know this, and you do know that, and so you can build it yourself, like I've already gone through, right? Sometimes, just kind of get a list of equations. It's just unmanageable. So it's nice to just be able to work from scratch on things sometimes, right? Not have to remember a new formula. Anyways, the numbers will just go in and give you the charge. So you look at that charge, and then you're like, okay, so remember we looked at before, like if we said, okay, if one electron, or the charge on an electron is 1.602 times 10 to the negative 19, it's supposed to be, oh, come on now. Did an undo there, but what's going on? Yeah, there we go, back on the page. 10 to the negative 19. It's just still trying to move me around here. Right, so we've got a ratio. And then so then I'm like, oh, 4.1 times 10 to the negative 16. Question is, how many electrons is it? And you're like, oh, well, I just have to divide by 1.602, right? So that's how we're going to figure out how many electrons. You would figure out how many electrons it really is, or how many of deficit. So the this here, it says, the charge on the droplet is 4.1 times 10 to the negative 16. It's an extremely small amount of coulombs, but that's actually about 3,000 electrons. If I do the numbers just quick here, that would be from the 4.1 e to the 16 negative, and then I need to multiply by 1.602 e to the 19 negative, and divide, sorry, 4.1, so I need to divide. But I'm getting a logical answer there, so I had to recheck my logic here. 16 negative, divide by 1.602 e to the 19 negative. I did 1 negative. Slow down. Yeah, the actual number is 2559.3 electrons. So obviously it's like, there must be that many electrons. And then this is your estimation, right? So knowing the charge of an electron allows you to figure out how many electrons it really was missing. What is it here? Does the electron have a deficit? Oh, this is the same things I just did. Now this page is using that Q equals NE. Do we need a formula Q equals NE? No, we just need to know the charge on an electron, and we know how to use ratios, right? So this is another example of a formula you can use if you want, but you don't need a formula. So depending on the number of significant digits, there's a worthwhile mention here. If it's actually only 2 SDs, then of course, if it's just 2 SDs, I'm really getting annoyed with my computer today. Okay, so if it's just 2 SDs, significant digits, of course, I'm meaning, then you would keep this part here, right? So you'd be like 2.5 or whatever. That's why they would have rounded like that, approximate and whatever, depending on what we had. Now that's not clear, by the way, though, because you have like all this stuff, right? So to me, it's like there's at least 3. Why not call this 2540, or leave it as, or just leave it like this, right? Because then it's questionable whether that 0 is significant or not. A little review of significant digits along the way as usual. So that is our discussion about parallel plates and the difference between what we had seen previously and so on. So 358 number 7. And bits and pieces here and there because your textbook kind of goes all over the map, all over the place. But that's stuff, all to do with the same thing, same stuff.
I wasn't really sure what you mean by like a deficit or an excess, like compared to what?
So you have an oil droplet. That's, yeah, I'll do that, no problem. So let's go to this slide here. And so picture an oil droplet. If it's neutral, right, would have plus, minus, plus, minus, plus, minus, all pairs, whatever. And so to become charged, so it would become positive, it would have to lose some, right? So instead of plus, minus, plus, minus, plus, minus, we'd have to get rid of some of the electrons. And so if I ungroup this thing here, picture having a deficit of, try again here, having a deficit of, say, 1 electron. So that would be, come on now, here we go. So that thing has a deficit of 1 electron, and now a deficit of, if I ungroup again, it'd be a deficit of 2 electrons, right? So this new oil droplet has a charge of +2. So this one's neutral, and then this one is +2. You with me now?
Yeah, that makes sense. Thank you.
Good deal. So of course the questions are always listed just in the homework page here, nice and easy because you have those files as PDFs. So those are for you to tackle next, and the solutions will be posted as always because I'm working my butt off to have them ready for you. It's actually, like I'm preparing these lessons, delivering these lessons, plus doing all the homework you guys are asked to do too. So I'm working hard for you. I hope it helps. Yeah, so that is that part. Let's see if we can tackle. That's one lesson, one grade 12, lesson. So let's see what we can get through for this part. I think we can do it. Ready for it? Well, too bad. Sorry. Whether you are or not, we're stuck with this quadmester nonsense. So here we go. But try your best and let me know how it's going. So motion of charged particles in uniform fields. So we are just looking at energy in these things, right? This is actually kind of a review of what we just looked at a little bit, but some applications, you can use this to make particle accelerators. So if you want to do particle physics and see what's inside of different types of particles, you smash them together with enough energy and see what happens and figure out the what's going on. So new physicists learn about particle physics, like what particles make up what. Similar to if to learn how fancy watches work, like Swiss-made watches, to learn how those work, you just basically throw them together hard enough that they break apart into 1,000 pieces, and then you look at those 1,000 pieces and see what there was, right? So that's actually what what particle physics is, where you smash them together and see what flies out and make conclusions based on that. Kind of weird, but that's why they need particle accelerators. Cathode ray tube television sets. So cathode ray tube television sets, this kind of old beast, if you have any of those or kicking around your house still, or if they've already maybe been given away at the curb, but there's a beam of electrons from the back here that's fired towards the front. And then there's a whole bunch of phosphors here that can glow red, green, or blue when an electron hits it. And if you fire them in the right spots, you get a picture of, whatever you want. Vladimir Guerrero hitting a home run or whatever. Been a lot of those lately, except they're like pitching outside on them now. And it's going to have to. Anyways. There's a baseball thing for you. The way they are directed, the way they're directed and so on is what we're going to be learning about in this lesson. Okay, so how we actually aim the electron beam. So to be a little more clear here, we've got what's called a thermionic emitter in the back. It heats up metal and it gives off electrons as a result. Those electrons are then accelerated forward, so you can picture how an electron would be accelerated easily. And then it gets, once the electron's moving, then it would have a set of parallel plates. Let's say here there's a parallel plate back here that has a hole in it in the middle, right? And so we've got a positive plate here and a negative plate there. So the electrons, first of all, get accelerated forward. Now you got an electron zipping along. And then if you want to steer it left, then you have plates on the left and the right. And if you want to steer it up and down, you have plates above and below, right? And you adjust the voltage to send the electron left or right, and then send it up or down. And you can get on the TV screen the electron to land wherever the heck you want it to. It's really quite an amazing feat of engineering that they were able to make this happen and do this back in the 70s. They even got color TV, and even earlier than that was black and white TV. I find it pretty amazing that they're able to send the signal for where all these pixels need to be lit up over the air with antennas, and then eventually by cable TV, and now by fiber optic. Like, it's pretty neat stuff. But that's how it works. An inkjet printer maybe you've had as well. They're not as common anymore. Most people are just lasers, but laser printers, but little droplets of ink, and then the ink gets charged, and then you deflect it up or down, and you deflect it left or right, and you aim little ink droplets at a page, and you get your letters of what you're trying to print out. Okay, so those are two examples of applications of parallel plates in the electric fields, and how we use them. Right, use the fact that we can change the direction of the charges. So here's just a calculation type question to do this. This is kind of review from the previous lesson, to be honest. So we've got a voltage applied across the plates. So see how I have this shown on here to be more clear. But when they said an electric potential difference of this, it did mean this. It's just not obvious enough for me, at least, anyways. So they are asking for you to determine the kinetic energy of the electron halfway to the positive plate. So the electron started here and went to here, and they're asking for the kinetic energy at that point. Okay. So they gave us the voltage, they gave us the charge because it's an electron, and they gave us, I guess maybe end up knowing the mass too, and so on eventually, right? So we'll list those things, but certainly we know the charge, and it's an electron, right? So this should have been a minus here. They just, where I got this from, they missed it. So for parallel plates, we know potential difference is energy per charge. So yeah. You know what? I would almost cross out for parallel plates here. It's not so much for parallel plates, just in general as a concept. But yeah, just in general as a concept, that's delta V equals delta E over Q. And so this is, I'll undo the cross out, but this is for all the way across, isn't it? Right? This is full voltage, so this is all the way across. Now, why didn't they automatically just say, you know what, if we're looking at, if we have this extra complication in the question of wanting to know halfway, why not just do that, divide by 2? But we'll see, it comes up. Of course, it's going to be half the energy, and so now they're dividing it by 2. So the idea we're relying on here, well, I'll undo that. I'll leave that there for now. But we're relying on this concept that the energy, the electric potential energy, is transferring to kinetic, right? And so that's why this number is equal to this number. More thoroughly written, it would be negative delta EE equals delta EK. That comes from, you're going to see this in detail soon in a new question, so I may as well show now too. The total energy of a system is the electric potential energy plus the kinetic energy, right? Give these two kinds of energy that are kind of switching spots. So if we say the change in each of these, that would still be true too. And the concept that we talked about in the past was that the change in the total energy is going to be 0 because energy is conserved. Okay, so this equation, this concept of conservation of energy leads to this, which leads to this. So they glossed over the fact that this is a negative, and then they also glossed over the fact that this is equal to the negative of delta E. So what happened there is we had 2 negatives. So this became a negative of a negative, so it became positive. Drives me crazy when things like that gloss over. I should modify this, I suppose, this page to have that detail in there, but maybe me showing it being missed helps you notice when it's missed and things that you see later on too, right? So maybe it's a win. Anyways, so the kinetic energy is going to be 1.92 times 10 to the negative 17. Okay. So that part there, we're good. Hopefully with that, it's just applying the concepts that we have learned about. That energy per charge transfers to be kinetic energy per charge, right? Electric energy per charge transfers to be kinetic energy per charge. Half of it because we're only going halfway. Weird little fact about this. If we look at the total velocity you'd get in comparison to the velocity of it halfway, the halfway point is not half the velocity. And this isn't something that's weird specific to electricity and charge plates and so on. This is a fact about anything that's accelerating. And the way you can think of this is as this electron accelerates to there, it's going slow. It's going stopped in the beginning, right? So it's going to take a while. It's going to take longer for it to get halfway than it does to get the rest of the way. Because here you're starting with 0 velocity, ending up with velocity of, let's say, 10 meters per second. Now you're going to go from 10 meters per second up to an even faster velocity, right? But it's not going to be 20. It's not going to be double because you have more time to accelerate in the first half than you do in the second half. So if this was 0, 10 meters per second, this might be like 14 or 15 or 16 or something meters per second. Okay, that's a weird counterintuitive thing that's just always true for uniform acceleration that you may or may not recall from grade 11. So notice that in the equation there's a square, there's a v squared. Well, if we look at it later on in 1/2 mv squared, right? I didn't write it in there, but I should. I was thinking it was on the page here, but it's not. So we're talking about 1/2 mv squared, EK equals 1/2 mv squared. And that square makes this weird reality of not having half the speed at halfway the way it is. Seriously. Computer driving me crazy. Right, so we got that square in there. Anyways, that's a reminder from previous classes. Yeah, just a reminder here, you can just work from scratch if you want as well. I'm not going to do it here because you need more information, but we could work from scratch since the force is constant. right? So you'd be like, well, if we had the distance between the plates, which we don't, so I can't actually do this. But if I did have it, then I'd be able to figure out the newtons per, right, the force per charge that would be on it. So this voltage divided by the distance would give me force per charge. And then I know the charge because it's an electron. And I know I can figure out that force value if I know the force value and I know the mass value, which we do because it's 9.11 times 10 to the negative 31 kilograms, right? Because it's an electron. So this would be 9.11 times 10 to the negative 31 kilograms. It's an electron. So you can see that we could work this out, but the final step might give you heart palpitations here, where you'd have to figure out the final velocity, right, using uniform acceleration work. So at this stage, I'm just kind of pointing it out to point out that it doesn't have to be as mysterious as this new stuff of voltage being energy per charge and you know, and so on. Like that seems unfamiliar, but in reality, it's coming from very familiar stuff, isn't it? This would agree with what we figured out here. So if we did know the distance between the plates, we'd be able to figure out the force. So we'd be able to figure out the acceleration. So we'd be able to figure out the velocity. It would be kind of cool, but I think I'd lose you. I think it'd be too many pages of big calculations to eventually end up saying, see, the velocity really is, you know, or the energy really is 1.92. Okay, so I just wanted to show the logic of that. So you could picture this journey of determining a value, using that to determine another value, using that to determine another value, and then finally determining the velocity if we wanted it, right? And then, of course, once we have velocity, you can figure out EK, right? And that EK would be the same number. It would be the whatever this was down here, 1.92 times 10 to the negative 17. Okay. So you can picture how that would be a good summary of all the stuff. We haven't done the refresher of this yet, so I certainly wouldn't expect you to do that right now. But I do expect you to sort of acknowledge, like, yeah, that makes sense. That's doable as long as I have that skill fresh in my mind. Any questions at this point? You know, you're going to go back to this later on and look and be like, yeah, they gave me information. I know to do with delta V and Q, and we're asking for essentially we need to first figure out delta EE, right? Because then that goes to EK. So that's how this equation was noticed. You look at what you're given, use an equations to do with it. Okay. So I don't know if we actually, do we calculate the velocity ever? Does it say to get the velocity? Oh no, it just says determine the kinetic energy. If we did want to get velocity, let me just add in if we wanted velocity, right? If it was asked for, of course, we'd use EK equals 1/2 mv squared. And again, the mass is known, the kinetic energy is known. Of course, we'd get the velocity, right? So I think I do that in the next question. I think. So if an electron, what's the speed? So the electric potential difference between parallel plates is 5.0 times 10 to the 3. They're telling us that it's 5,000 volts applied across the plates. So it's actually a delta V, right? So electric potential difference, delta V, because of the difference. It's because it says difference here. We're talking about delta V. Whatever. So let's start out with, they're asking if an electron's accelerated from rest at the negative plate all the way to the positive plate, what would be the speed? So this is one where we're going to do that same kind of work again, where we're going to get the energy and then we're going to get the speed. So we know the energy, again, is still this formula, right? The potential difference is change in energy per charge. So we're able to calculate right away that the energy is 8 times 10 to the negative 16. That one seems a little different because what they gave us, oh no, it's the exact same. Yeah, the exact same. So the charge times the energy per charge gives you the energy, of course. So they're saying starting at the negative plate, of course, it's going to have lots of potential energy. It's going to convert out to the other, to kinetic energy. They're talking about conservation of energy like I've talked about. So we've got the energy equals 1/2 mv squared. The mass of the electron, all the values get plugged in there. They rearranged and then solved. You could have, of course, just put in the 9.1 times 10 to the negative 31, and you could have put in, well, I guess put the number in and then start to solve. To me, I find that easier to follow. But they obviously multiplied both sides by 2. That's why that's over here, because a 2 and a 2 gets rid of it, right? And so on and so on. And then divided by mass, and eventually rooted, which they didn't show, but we can tell they did it. Root and root. Wow. So they got an answer of 4.2 times 10 to the 7 meters per second. Okay, so I want to just mention something right off the bat. Okay, they're saying that it would strike with a velocity of 4.2 times 10 to the 7. They are pointing out that that's a tremendously large velocity. It's huge. It's close to what's referred to as the speed of light. It's over 10% of the speed of light. We are going to see as part of this course that means some weird, wild stuff would start to happen. So due to the large velocity, since it's a substantial fraction of the speed of light, there's actually a correction needed in calculating that velocity. So we'll actually look at that later in the course. So what happens is as it's speeding up, getting really, really fast, special relativity effects start to kick in. And yeah, we'll cover that nicely. Halfway, half energy, velocity, right? So there's the kinetic energy equation, half of the energy plugged in. Notice the velocity is more than half of the 4.2. That shouldn't be a surprise, right? So it gets to almost 3 in the middle. Picture the parallel plates. And we had an electron repelling away. Is that what it was? Yeah, an electron repelling away from a negative plate. As it goes to here, we get 4.2, or sorry, we get 3. As it goes to the middle, it gets 3, meters per second. And then in the end, it's only 4.2, right? Because it had more time to accelerate on the first half of the journey. The second half of the journey, it's going much faster, so it doesn't have so much time to accelerate. So that is almost the exact same question as the one we just did. So hopefully that repetition helps sink that in a little bit for you. So the other situation that is kind of actually more common, we've been dealing with a special case, right? This whole parallel plates business. That's a special case where you have uniform motion and so on. So we had this special, equation kind of to do with it, where we could just, delta V or delta V over Q, and the potential difference applied. The more common situation in the universe, of course, is when you have non-uniform electric fields, right? So when you have just a charge, you have non-uniform fields. And so here, remember we talked before about here, there's 2 field lines. And so here there's only 1 field line with a similar size circle. You can tell this is a weaker electric field strength. And so this is a non-uniform electric field. And so of course the force is not constant, right? So they're showing here if a positive test charge is placed next to a positive charge, it'll be repelled, but of course it's non-uniform, and so the force doesn't remain the same. So according to Coulomb's law, as the further you get by the square of the distance, the force is going to get less, and so on. So we would have trouble, this middle paragraph here, we would have trouble analyzing this directly because we wouldn't have constant motion. Okay, so we cannot easily apply Newton's second law and uniform acceleration because acceleration is not constant. Okay, so instead, we're just going to use the energy concepts. We're going to say, well, the energy at the final location minus the energy at the initial location is going to give us a delta E, and the delta E is going to become delta EK. So it's actually pretty easy when you think of it that way. It's just we have to use the correct formulas for energy, right? Because it's not uniform. So you understand the difference between what we're doing there? I think it's just non-uniform. So we're going to look at, remember, EE is the K, Q, Q over R, right? So that's a known formula that we've seen in the past. So we just have to do the difference between one spot and the other, and that's the kinetic. So to me, it's not that crazy of a thing. It's still one energy form transferring to another. That was called the work energy theorem, by the way, in grade 11. Energy of one form transferring to another form. So here's an example. I'll explain it rather than having to read all the words, but later on read the words and see that it does mean what I'm saying. But they're saying this A is fixed in place, and then B is free to move. So B is feeling the effects of the electric field of A, essentially is what's going on. So it's going to repel because they're both negative charges, right? So what we're going to do is we're going to figure out the electric potential energy it has at the final position, and we're going to subtract from that the electric potential energy it has at the initial position. That's going to be the change in energy. That's going to be what transfers to kinetic energy. We're going to figure out the velocity. So it's not as crazy as it might seem if your head's spinning a bit. Yeah, so I'm showing on this page the idea of conservation of energy rather than just saying it the way I did here, where the difference in the energy becomes the kinetic. I'm trying to be more thorough with that. So they basically say like the energy, and the way this was started out here anyways, I should say, is the initial energy is equal to the final energy. So energy is conserved, or they list it as E equals E prime. That's just another way of saying that. So notice that prime up here, the green, prime or apostrophe, they call it prime, means final. So E equals E prime or E apostrophe means initial equals final. I don't like it either, I admit, right? So many different ways to show things. But of course, I'm trying to train you to, teach you to recognize all these different things. So they are saying that the initial energy equals these final forms of energy, right? We've got a final form of energy of electric potential and kinetic. The initial energy would be the potential energy based on the initial distance. So the initial distance was 0.45 meters. So you're going to see a 0.45 on, well, if they put the numbers in first, you would see a 0.45 on this side, right? The final position was the new position of 0.45 and then an extra distance out. What does it do here? 0.5 meters per move when it reaches a distance of 1, right? So we'd have a 1 for that final position. So picture a 1 plugged in for this other one. So this is 0.45 here, and this is going to win as a 1. And you're going to see those on the next page where they've algebraically manipulated it. Eventually, they're going to put numbers in, but so there now is the 0.45 and the 1. Again, I could totally rejig this page and have it just be easier to follow, but you're kind of forced to try and follow stuff like this in textbooks and other people's work and so on, right? And maybe this is the way you prefer it too. There's lots of different ways to think of this. So far, I'd say that's what we've got there. I'm going to come back to this in a bit, but yeah, this. Well, actually, I'll show it right now. It's kind of weird. Notice that that's the initial energy. Take away the final energy, right? Which normally we'd say the change is final minus initial. That's just, but the way this is working out does actually follow step by step. So then the numbers in there are what I was showing. Remember I said this is the 0.45 and that's the 1. There's the 0.45 and there's the 1. They've just common factored out the K's and the Q's. So bring those guys outside, bring them out, opposite of distributive law, basically. So there they are outside, boom, boom, boom. And we've got an easy, just a bunch of math to do right at that point. Just calculate and get numbers. So your calculator works, you could do it, no worries. So that gives you numbers, which gives you other numbers. You're rooting both sides. You get the velocity be 168.6 meters per second. this shouldn't be that big of a deal, really. It's just change energy. It's just the way it's shown is a little different. So it's good to see it different ways, right? I normally would say this where it's like the idea of, you know, delta E. And so when we have my way I've said it before was on the previous page, there was the change in the total energy equals the change in the electric plus the change in the kinetic. And that led to that the change in the EK is equal to the negative of the delta E. That's this right here, right? When you subtract it over, because this is 0. So this negative EK thing leads to what they had here, right? Because this is final minus initial. But guess what? Negative of, right? Negative of final minus initial leads to initial minus final. So you can see the equivalence between the sort of the new way right here. The new way they're kind of showing it versus how you may be more accustomed to seeing it, because this is initial minus final in there. For that reason. So that they're rounding based on significant digits, who cares? But yeah, so they're saying that, you know, when it's 1 meter away, it'll have a velocity of 170. So we're still able to calculate velocities, even though it's a non-uniform electric field. Okay. I have a note there saying see page 366. There's another example just like this. I even copied it into the lesson for you to make it easier for you to find it. So if you want to see another one all worked out, go for it. It's there for you. Oh, this is a little more notes about that weird stuff to do with potential energy, right? Or total energy. So I'm showing very thoroughly the idea of the total energy equals each energy added up. So the change in each is also equal. The change is 0 since energy is conserved, blah, 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 blah. Right? So you're talking about a negative delta E, which is why it ends up being initial minus final in that calculation. So I think that's pretty much it, because this is just the same question worked out. This one is a little cleaner and a little easier, just ideas. So we have, you know, officially 7 minutes left of our reduced time, plus that extra half an hour of class time that I will be logging in at 1 o'clock for you if you need extra help. So we have dying minutes to just think through the logic of this. If we've got a positive charge particle and we've got a positively charged particle that's fixed in place. So we've got the one that's causing the field, and then we've got the one that's responding. So this one's causing the electric field. You know, maybe do it like that. This one's the one that's affected by it. This one's affected by the field. Sloppy. Anyways, so what's the net force? Well, what's the net force of the moving charge? Positive repels and fixed in place. What happens? Oh, this is as it repels, what happens to the net force? So it's getting farther and farther away. So of course the force is going to get smaller and smaller because it's farther and farther away. We know that Fe equals KQQ over R squared. And so this is going to get bigger, right? This gets bigger. So overall, Fe gets smaller. What about the acceleration then? Well, if the force is getting smaller, of course the acceleration is going to get smaller. What about the speed? Well, they say here, actually, it's a good idea to, I'm going to show it like this. So it decreases because of Coulomb's law. We're getting farther apart, as I showed, right? The acceleration is going to decrease. They say, in this case, oh yeah, they're basically saying here, this velocity is increasing, of course. Now, even though the acceleration is decreasing, it's still speeding up, right? It's just speeding up at a slower and slower rate as it's repelled away. It's the negative one where I have an extra thing that I want to show. What about the electric potential energy? The electric potential energy is decreasing because it's transferring to be kinetic. Okay. So what happens in this case is it's becoming a smaller and smaller positive value. It's decreasing. I'm making that note because in the negative case, it's weirder to talk about. Okay. But in this case here, where we have a positive near a positive, right? We're talking about a case where we have positive EE. Okay, it's the one that looked like this on the graph. Okay, so when we're going farther and farther away, we're talking about this. We're talking about it's repelling away, it's going farther and farther away. There's your distance, there's your electric field, something like that. And that's actually supposed to be EE, I guess, right? Yeah. And then the kinetic energy, of course, is increasing, right? Because it's repelling, it's picking up kinetic energy. So the one I want to make sure to talk about is the negative one, because it's a little weirder. So this is the one where we're talking about a graph that looks like this. So we're talking about the electric potential energy it has as you move away. So as we move away, we're doing this. Okay. So when you're attracted to something, you're stuck to them. You need to get energy, right? I need to add energy to get out, right? So we're adding energy to go this way. But notice that we're adding energy and ending up at 0. Eventually, we end up at 0 joules. So we have a negative energy, right? So maybe a negative number like negative 20, right? Once I add 20, I get to infinity at 0. Negative 20 plus 20 equals 0. Right, so that's the idea of negative energies. I definitely remember that boggling my mind when I first learned it. Okay, so just try to get your head around the logic of that. Is that you have right now you have negative gravitational potential energy right now, because in order for you to escape Earth's gravitational field, you would have to, of course, have a whole bunch of energy applied to you in the form of like a rocket, courtesy of Elon Musk, you know, if you're going to Mars or something. So you need to add a bunch of energy to you to get to 0 energy relative to Earth. So net force, of course, would what? So net force, what does this one say? Negative particle attracts, yeah, so as we attract towards, so I apologize on my arrow direction here. This question is talking about the other case. I focused on the idea of going away from it, just like the other question by accident. We're saying attracting towards, so we're talking about going this way. Okay, the green stuff that I talked about was for escaping. Okay. Anyways, so when we're attracting, obviously the force is going to get bigger and bigger because you're getting closer and closer. So the acceleration is going to get bigger and bigger because you're getting closer and closer. And then it says the speed. Well, it says it's increasing since it's accelerating. This is what bothers me. It's increasing since it's accelerating. My question is to do with that. Does acceleration always mean that the speed increases? The answer is no. Sometimes acceleration can cause things to slow down, right? So I would want you to add in, since it's accelerating in the direction of motion, right? Since it's accelerating in the direction of motion is an important clarification. Electric potential energy. What's happening to the electric potential energy as we go closer and closer? So it's going to a bigger and bigger negative value. That's the correctest way of saying it. It's going to a bigger and bigger negative value, but that actually means that it's decreasing, which sucks. Okay, you're saying the energy is decreasing by going to be a bigger and bigger negative value. So, you know, you're getting a bigger negative value, so that kind of seems like it's increasing, but sorry, it's not, it's decreasing. And then the kinetic energy, what's happening? Well, it's speeding up, right? It's increasing. So picture being at a negative 20 joules, and then as you go in towards it, you get to like a negative 50 joules, right? So this decreased by negative 30, which corresponds to an increase. Basically, that negative 30 transferred to, right? So we had 30, a drop of 30 and a gain of 30. So a drop of 30 corresponding to a gain of 30 of kinetic. And that is it. Tomorrow we're starting with magnetic stuff, and it'll be a little bit of a breather from these new equations. This, by the way, look at one question there, 2 questions there, 1 question there, 1 question there. So if you're freaking out right now, relax a little bit. 1, 2, 3, 4, 5, 6, 7, 8. No, it's only 9 questions. For you course, you're looking at, it's supposed to be, yeah, they say like 40 minutes of homework to do with each class. That's the going rate, right? And since we did 2 classes, plus we still have another half-hour class, I apologize if it feels like I'm killing you, but this is the curriculum. This is the course. So I am definitely willing to work very hard to try and help you. Use me. Okay. So I will log in again at 1, and we are over time and done. Alrighty. So have a good rest of your day, and I will log in at 1 and help as much as you would like.
Thanks.
You're welcome.